Hello, dear listener. Welcome. As the day softly recedes and the quiet darkness begins its gentle embrace, let us turn our thoughts, not inward, but outward, far, far out, into the boundless expanse that cradles all existence. Tonight, we will journey together into the concept of space. A word so simple, yet holding such profound mystery, such immense depth, and such endless wonder. Allow your breath to deepen, your shoulders to soften, and your mind to simply float with these ideas. Space, in its most fundamental understanding, is often described as a three-dimensional continuum. Just imagine, for a moment, the room you are in. You can move forward and backward, left and right, up and down. These are our familiar three dimensions. They define where you are, where you can go, and where everything else resides. It's the stage upon which all physical reality plays out, a canvas of positions and directions that allows for the dance of particles, planets, and even people. In the gentle, classical view of physics, this physical space was often conceived as precisely these three linear dimensions, distinct and separate, a container for all things. But as our understanding of the universe evolved, as we began to gaze more deeply into its intricate workings, our perception of space began to unfurl, revealing even greater complexity and a captivating interconnectedness. Modern physicists, those who peer into the deepest secrets of reality, usually consider space not as something separate, but intimately woven together with time. They see it as part of a boundless four-dimensional continuum, a fabric known as space-time. Imagine time not as a separate river flowing by, but as another thread in this cosmic tapestry, inextricably linked with the threads of space. Every event, every moment, every movement, exists not just at a certain place, but also at a certain time, forming a single, elegant entity. This concept of space-time invites us to contemplate a universe where motion through space is always accompanied by motion through time, a continuous, unfolding story within a single, unified framework. This idea, this profound concept of space, whether as a three-dimensional container or a four-dimensional continuum of space-time, is considered to be of absolutely fundamental importance to an understanding of the entire physical universe. Without space, there would be nowhere for anything to be. Without its properties, the very structure of reality would crumble. It is the very framework upon which all other physical laws are built. Yet, despite its undeniable centrality, a beautiful and enduring disagreement continues to echo among philosophers, much like distant stars whispering secrets across the void. They ponder, is space itself an entity, a real, tangible thing that exists independently? Or is it merely a relationship between entities, an abstract way we describe how objects are arranged relative to one another? Or, perhaps, is it part of a conceptual framework, something constructed by our minds, a lens through which we perceive and organize our experiences of the outside world? These are not questions with easy answers, and their very existence invites us to simply ponder, to allow our minds to explore the edges of what we think we know, without needing to arrive at a definitive conclusion right now. Just breathe, and let these questions gently settle around you. As centuries turned and human thought progressed, particularly in the 19th and 20th centuries, mathematicians, those architects of abstract thought, began to examine geometries that were radically different from what was traditionally understood. They ventured beyond what we call Euclidean geometry. In the Euclidean world, the space we are most familiar with, space is conceived as flat. Imagine a perfectly smooth, infinite tabletop. Lines can be drawn, triangles formed, and all the rules of geometry we learn in school hold true. It's a very intuitive, comforting flatness. However, these mathematicians dared to imagine something else entirely. They conceived of non-Euclidean geometries, in which space is thought of as curved, rather than flat. Picture, instead of that flat tabletop, the surface of a giant sphere. If you were an ant walking on it, your straight line would actually be a curve following the sphere's surface. The sum of the angles in a triangle drawn on this curved surface would not be 180 degrees. This might seem like a mere mathematical abstraction, but it took on breathtaking physical significance with the genius of Albert Einstein. According to his revolutionary theory of general relativity, space around gravitational fields does indeed deviate from this familiar Euclidean flatness. Massive objects, like planets, stars, and galaxies, don't just pull things towards them through some mysterious force. Instead, they gently, but profoundly, warp or curve the fabric of spacetime around them. Imagine placing a heavy bowling ball on a stretched rubber sheet. The sheet dips, creating a curve. Now, if you roll a smaller marble nearby, it won't just roll past. It will be drawn towards the bowling ball, not by a pull, but by the slope, the curvature, in the sheet. This is a simple, tangible analogy for how gravity works according to Einstein. Planets orbit stars not because of an invisible rope, but because they are simply following the curves in spacetime created by the star's immense mass. And this isn't just a beautiful theory. Experimental tests of general relativity have, over and over again, confirmed that non-Euclidean geometries provide a better, more accurate model for the actual shape of space, particularly in the vicinity of massive celestial bodies. So, when you look up at the night sky, you're not just seeing objects in a flat, empty box. You're witnessing the graceful dance of matter moving along the gentle undulations and curves of a truly magnificent, dynamic cosmos. Let that thought wash over you, the universe as a vast, undulating ocean, rather than a rigid structure. Now, let us drift back through time, exploring the whispers and shouts of thinkers who have grappled with the profound nature of space for millennia. The debates concerning the very essence of space, its mode of existence, its deepest nature, stretch back into the mists of antiquity. We can hear echoes of these discussions in ancient treatises, like the Timaeus of Plato, where he mused about the role of a receptacle or chora, a kind of space, that holds all created things. Or in the thoughtful reflections of Socrates, as he pondered what the Greeks called chora, which loosely translates to space or place, questioning what this fundamental container truly was. Aristotle, in his Physics, in a specific section known as Book 4, Delta, meticulously defined topos, or place. For Aristotle, a place wasn't an empty void, but rather the inner boundary of a surrounding body. Think of a fish in water. Its place is defined by the water immediately surrounding it, not by an abstract, empty volume. These were deeply rooted, intuitive ways of understanding where things belong, and where they were. Later, in the 11th century, a brilliant Arab polymath named Alhazen, known for his groundbreaking work in optics, brought forth a geometrical conception of place that redefined it as space qua extension. He began to view space more abstractly, as a measurable expanse, a quantity that things occupied, moving away from Aristotle's more localized, relational definition. It was a subtle but significant shift, paving the way for later, more mathematical understandings. Many of these classical philosophical questions, these ancient ponderings on the nature of space, were rekindled and intensely discussed during the vibrant intellectual ferment of the Renaissance. And then, they were powerfully reformulated in the 17th century, a period of immense intellectual awakening, particularly during the early foundation development of classical mechanics, the science of motion and forces. It was during this era that two titans of thought, Isaac Newton and Gottfried Leibniz, offered strikingly different, yet equally compelling, visions of space. Imagine, if you will, Newton's view of space as an absolute entity. For Newton, space was like a vast, invisible, unchanging stage, existing permanently and independently of whether there was any matter within it. It was an infinite, empty canvas, always there, always ready to host the grand cosmic drama of planets and stars, utterly unaffected by their presence or absence. It was the fundamental container, eternal and immovable, an omnipresent presence, a divine sensorium, as he sometimes hinted. This absolute space provided the fixed reference frame against which all motion could be measured. It was a serene, silent, and infinitely deep backdrop for everything that ever was or ever would be. Let this image of absolute, quiet vastness gently fill your mind for a moment. In contrast, other natural philosophers, most notably Gottfried Leibniz, held a profoundly different perspective. Leibniz thought that space was not, in fact, an entity in itself, not a separate thing. Instead, he believed that space was a collection of relations between objects, given by their distance and direction from one another. Think of it like this: if you remove all the objects from the universe, if there were nothing at all, then for Leibniz, there would be no space. Space is the order of coexisting things. It's the pattern, the arrangement, the network of relationships that exist between physical objects. It's like the music played by the orchestra, rather than the empty concert hall itself. This relational view suggests a deeply interconnected universe, where space emerges from the very existence and arrangement of matter, a beautiful web of dependencies. In the 18th century, the philosopher and theologian George Berkeley added another intriguing layer to this debate. He attempted to refute what he called the visibility of spatial depth. In his essay Towards a New Theory of Vision, Berkeley argued that we don't directly see distance or depth. Rather, we infer it through our experiences, through touch, through muscle movements, through the convergence of our eyes. This challenged the intuitive idea that space is something we simply perceive directly, suggesting that even our basic perception of space is a construction of our minds and experiences. And then, the profound metaphysician Immanuel Kant entered the stage, offering a truly revolutionary perspective that continues to resonate today. Kant proposed that the concepts of space and time are not empirical ones, not things we derive from our experiences of the outside world. Instead, he argued, they are elements of an already given systematic framework that humans possess and use to structure all experiences. They are, he posited, inherent structures of our own minds. Imagine your mind as having a particular set of spectacles through which it must view reality. These spectacles, for Kant, impose the forms of space and time onto everything you perceive. You cannot help but experience things in space and in time, because these are the very conditions under which your mind operates. Kant referred to the experience of space, in his monumental critique of pure reason, as being a subjective, pure a priori form of intuition. A priori means prior to experience, it's built in. Intuition here refers to the way we directly apprehend objects. So, space isn't out there, an objective container existing independently of us. Rather, it's a fundamental way our minds organize and make sense of the sensory information we receive. This is a deeply calming thought. The very structure of the universe, as we perceive it, is shaped by the structure of our own consciousness. The cosmos we see is, in a profound sense, also a cosmos within. This brings us to the very foundations of the scientific revolution, a period of breathtaking discovery that reshaped our understanding of the cosmos. The Galilean and Cartesian theories about space, matter, and motion are truly at the bedrock of this revolution, a period understood to have culminated with the triumphant publication of Newton's Principia Mathematica in 1687. Newton's theories about space and time, building upon these earlier insights, were instrumental in his ability to explain the precise movement of objects, from falling apples to orbiting moons. While his theory of space is considered the most influential in physics for centuries, it emerged from, and indeed refined, the ideas of his brilliant predecessors. Let us turn our gaze to one of these pioneers, Galileo Galilei. With his revolutionary telescope, Galileo revised the established Aristotelian and Ptolemaic ideas that had held sway for millennia, ideas about a geocentric cosmos, one with the Earth firmly, majestically, at its center. This was a worldview deeply embedded in human intuition and religious belief. But Galileo, through careful observation and daring deduction, backed the Copernican theory that the universe was, in fact, heliocentric. He envisioned a cosmos with a stationary sun at its radiant heart, and the planets, including our own beloved Earth, revolving gracefully around this central star. This was a radical, almost terrifying, idea for its time. If the Earth truly moved, then the deeply held Aristotelian belief that its natural tendency was to remain at rest was fundamentally called into question. Galileo, with his keen intellect, wanted to prove instead that motion was as natural to an object as the state of rest. He observed the sunspots, demonstrating that the sun itself moved around its axis. For Galileo, celestial bodies, including the Earth, were naturally inclined to move in circles, a perfect, eternal motion that reflected their celestial nature. This groundbreaking view gently, yet irrevocably, displaced another deeply ingrained Aristotelian idea, the notion that all objects gravitated towards their designated natural place of belonging, an idea that placed the Earth uniquely at the center, as the ultimate down. Galileo showed us a dynamic, dancing universe, where motion itself was a fundamental, inherent quality. And then there was René Descartes, a towering figure in philosophy and mathematics, whose systematic mind sought to entirely replace the Aristotelian worldview with a comprehensive theory about space and motion, meticulously determined by natural laws. In essence, he sought a metaphysical foundation, a mechanical explanation, for his theories about matter and motion. Descartes' vision of space was distinctly Euclidean in its structure. It was infinite, uniform, and flat. Imagine a perfectly smooth, unending canvas stretching in every direction, without any bumps, or edges, or limits. Crucially, for Descartes, space was defined as that which contained matter. And conversely, matter, by its very definition, had a spatial extension. This meant there was no such thing as truly empty space, no void. The universe, for Descartes, was a plenum, entirely full of matter, an infinite, continuous expanse of substance. This is a comforting thought, no emptiness, just continuous, flowing existence. The Cartesian notion of space is closely linked to his theories about the very nature of the body, mind, and matter. He is, of course, famously known for his declaration, "Cogito ergo sum, I think, therefore I am." This profound insight expressed the idea that we can only be truly certain of the fact that we can doubt, and therefore we think, and therefore we exist. In the face of a potentially illusory world, the certainty of our own conscious thought became the anchor of reality. His theories belong to the rationalist tradition, which attributes fundamental knowledge about the world not primarily to our sensory experiences, as the empiricists believed, but to our innate ability to think, to reason, to deduce. He posited a clear and distinct separation between the body and the mind, a concept famously referred to as Cartesian dualism. So, even as the body occupies space, the mind, the thinking essence, could be conceived as distinct from it, observing the vast spatial expanse. So, as we have gently traversed this landscape of thought, from the ancient Greeks pondering Cora, to Newton's absolute stage, Leibniz's relational web, Kant's subjective framework, and the scientific revolutions of Galileo and Descartes, we see that space is not merely an inert backdrop. It is a concept imbued with deep philosophical questions, a canvas of scientific exploration, and a source of endless wonder. Whether you imagine space as a boundless, unmoving container, or as a dynamic, curving fabric woven with time, or as a profound framework inherent in your own mind, these contemplations can lead us to a deeper sense of peace and belonging within the universe. It reminds us of the interconnectedness of all things, from the smallest particle to the grandest galaxy, and how our very consciousness plays a role in understanding it all. Allow yourself now to gently drift. The questions about space, its nature, its very existence, can remain as soft whispers in the background of your mind, without needing answers. Feel the gentle pull of gravity, a testament to the curvature of space-time. Feel the quiet rhythm of your breath, a small, yet profound, expression of your existence within this magnificent, mysterious expanse. Rest now, dear listener. Let the vastness of space cradle your dreams. May your night be filled with peace, quietude, and a sense of gentle wonder. Sleep deeply,